So without wasting time, I'm going to start with today's question. This is from a person called Rolinda Rorisang Mukuma. And her question says, so she's given us an equation, and it is, we have COBr2, and it is a gas. Now remember, when we are doing Kc, or when we're calculating Kc, it's very important that we remember that we do not include solids, but we do include gases and no liquids as well. So this is a chemical equation that we are given. And remember what I stressed with you guys last week, that you must always make sure that your chemical equation is balanced. In this case, thank you, Rorisang, but your chemical equation is balanced. Now let's see what they require us to do. So now this question is telling us initially, we have COBr2 gas, which is sealed. Now remember, we talked about an open containers and sealed and so forth, and the difference with them last week, sealed in a 2dm3 cubic decimeter. Now, with some of the questions that I've gotten today, you'll see or you'll find that the volume is not converted to cubic decimeters. So something that you must always remember when we are doing or when we're working with physical sciences or in chemistry, we work with the same SI unit. For an example, if you are in the States and let's use America, they usually use a gallon of milk where we use a liter of milk. So in South Africa, the correct SI unit for liquids, we use liters. In chemistry, when we talk about volume, it has to be in cubic decimeters. Sometimes they will add some spice and put it in milliliters or in cubic centimeters, but that means you will have to go and actually convert it to the correct SI unit. Now remember, in grade 12, if you cannot convert, the examiner will take it, or they'll think you don't know what's going on. So you might get negative marking or you might be penalized. And I mean, this is very easy stuff, so you don't want to mess all your marks on that. So in this case, our volume is correct. It's 2 cubic decimeter, sealed in a 2 cubic decimeter container. And it is heated. It is heated to 73 degrees Celsius. Just to add a bit of spice, sometimes they will ask you to convert degrees Celsius to Kelvin. Now, when we move from degrees Celsius to Kelvin, you just add 273, and that'll give you the value of Kelvin. And vice versa. If they've given you the degrees Celsius in Kelvin, they want you to move to degrees Celsius, or the temperature rather in Kelvin, wanting you to move to degrees Celsius, you'll just subtract 273. So the reaction is allowed to reach equilibrium with the temperature. And now they're telling us something nice. They're telling us that the equilibrium constant for the reaction, now we have to work backwards. Already you can see, is 0.19. Now, another thing, when we talk about chemical equilibrium, there are 3 ways in which they can ask you a question. The first one is like this one, where they actually give you the Kc and they want you to solve an unknown molar mass or something that was going on, maybe how much was initially put in or how much was actually used during the reaction. Or they can ask you to find one of the moles, or they can just make 2 things X. So it's usually one of 3 ways in which they can ask you this. And hopefully we actually cover all 3 today. So in this case, we have 0.19. And now the question that I've got, I'm just going to name this A. It says we must calculate the equilibrium. We must calculate the equilibrium concentration. The equilibrium concentration for COBr2 gas. It's actually very, very simple. I'm just going to go down a little bit. Let me rewrite this quickly. So the equation that we have is COBr2 gas. It is in equilibrium. Remember, we spoke about this last week where we showed that these 2 lines show that things are in equilibrium. Gas plus, here I've got Br2 gas. Now, I'm going to show you one of my easiest methods actually of how to work with this. So in most classrooms, some teachers use the start method, some teachers use the ICU method. I just use start, used, and equilibrium. So with this one, look, this is what we told, or this is how I would do it. I would say, or I usually say start, that's what we started with. This is what we've used. And what do we have at equilibrium? So now, Rorisang's question tells me that at equilibrium, it's found that 1.2 grams of CO2 is present in the container. So at equilibrium, so CO2 is CO2. I'm not going to write by start, I'm not going to write by use, but at equilibrium, it is said that we have 1.12 grams of CO2. Now, already you can see that the examiners try to spice it up for us because we don't work with grams when we do chemical equilibrium or when we are calculating. However, we have to use moles. Now, you're asking me, Tops, but now how do I move from moles, from grams to moles? So this is step numero uno. Before you can actually start calculating on this table, you have to move the grams to moles. And this is how we're going to do it. I'm going to show you guys two ways of doing it. My first method, if I have 1.12 grams of CO, I know for every 1 mole of CO, it is equivalent. Now I have to calculate. Now remember, in grade 10, we talked about molar mass and molality and so forth. So this is what we're going to be calculating. I know that CO is made of carbon and oxygen. Carbon, I have 1 carbon, which I'm going to add to an oxygen. If you look on your periodic table, carbon has a molar mass of 12 and oxygen has a molar mass of 16. When you add these two together, you get 28 grams for CO2. So 1 mole of CO2 is equivalent to 28 grams of CO. Now, I can cancel grams of CO with grams of CO, and I'm left with the moles of CO. Let me just cancel that. Now, my final answer for this one, let's calculate that. Whoopsie daisy. So, I have always put it in brackets, and always make sure that you actually have your brackets, because sometimes mathematics or the numbers will just do other things. 1.12, I'm going to divide that by 28. Remember to always press SD so that we can work with decimals. I get 0. I get 0.04 moles. Now remember, that's the SI unit there. I'm left with moles of CO. So now we've actually converted the grams to the moles. Now we just plug in. Another thing to remember when you're working with this, you've got ratios. This is 1, and this is 1. So initially, I'm just going to remove this whole piece here. So hopefully you guys will remember so that I can actually work properly and it doesn't look so cluttered. But at equilibrium, we have 0.04 moles of the CO. But looking at my ratios, remember last week we spoke about baking a cake? It's a ratio of 1:1:1 because there's no number in front of any of the molecules. So it means at equilibrium, if I have a mole ratio of 0.04, it means I'm also going to have a mole ratio of 0.04 moles on this side. Now remember, if this was what was put in, it was being used up, meaning on this side we were making, or it was adding. Initially, we have nothing. Remember, when you're baking a cake and you're still mixing your flour and your milk and your eggs and everything, you don't have cupcakes yet. So 0 cupcakes, but you do have ingredients. So in this case, we don't know what ingredients we're using. We know that we don't have products yet, but we know eventually when the reaction started occurring, at the end, we had 0.04 moles, which means we should have also used 0.04. And again, for the diatomic BR, we also used 0.04, right? But this is the one that is then unknown. Let's cancel this one quickly. So now, moving on, or actually filling up the table is one step there. Now let's continue. At equilibrium, I don't know what this one is. That's what Rorisang's question is telling us, that we must calculate the equilibrium concentration of COBr2. So this is what we are looking for. But now they've given us our KC. Now let's continue. Now remember, when you're calculating your concentration, we first say C is equal to N over V. I know it gets boring, but always write the formula. Unfortunately, when you are actually answering such questions, you do get marks for answering the formula. So my moles at equilibrium is 0.04. And I am told, when we look at Rory Sang's question, that it is in a 2 cubic decimeter container, which is my volume. And we've already said or established that it's correct. I'm also going to do the same for this one. And then we're going to calculate. N represents your moles, which is 0.04. Remember, these are the moles at equilibrium, at the end of the reaction. All over, it's in the same container. It's also in a cylinder that is 2 cubic decimeters. Let's calculate this one. So if I have 0.04 and I divide that by 2, remember to say ST, I have 0, I have 0.02, and remember when we measure, with the SI unit for concentration now changes. Remember when we do moles, it's moles. When we talk about grams, it's grams. But now when we talk about concentrations, it's mole per cubic decimeter. So we say mole dot dm3. Now this is the same, so I'm going to have 0.02, and it also will be mole dot cubic decimeter. So I do have that. However, I still don't know this one. That's the one that I'm looking for. But I know I have Kc, so it means I only have one unknown. Remember, when we're doing, let's say, vertical projectile motion, or we're doing pulley systems and whatever, you can have two unknowns and then you can use simultaneous equations. But in this case, when we have the equilibrium for the reactant that's unknown, but they've given you Kc, only gives you one unknown. So now let's calculate Kc. Now I know the formula for Kc. I always write this down. I should also teach my kids. You always have your products. You have your products all over your reactants. All over your reactants. I'm just going to plug it in as it is. Remember, on your left-hand side, you have your reactants. On your right-hand side is where you have your products. So my products always use square brackets. A shortcut, or when scientists are actually lazy to write, they use the square brackets to indicate that something is in concentration, or square brackets rather represent concentration when we're doing chemistry or chemical equilibrium. You'll see when you get to university, they stop writing the word concentration and just put brackets. So now these brackets represent concentration. We've calculated our values at concentration. So for CO, I have 0.02. For BR, I also have 0.02. All over, my reactant is the one that I don't have, which is COBr2. Looking at this question, they told us that the equilibrium constant for the reaction is 0.19. This tells us that the Kc value for this is 0.19. Now we're just going to do mathematics. Now, guys, you can take a shortcut, but number one, you do get marks for the step. So for example, if this question was going for 6 marks, hypothetically, they could say every step is a mark. So if you only have an answer, if you just plug this in your calculator, you might just get 1 mark. So you do want to show the examiner you understand your mathematics, you understand your principles, and how did you get to the correct answer. So I'm going to do it the long way around so that you know what I'm doing. So I'm going to start on this side. I'm going to say 0.19 equals, I'm going to multiply these two. So I'm going to have, put on a bracket, 0.02 multiplied by 0.02, and then I get 4 times 10 to the negative 4, so I get 4. Here's my pen. I'm going to get 4 times 10 to the negative 4 all over the COBr2 that I'm looking for. Now, here I've got a whole number. This side I'm working with fractions. You put this over an invisible 1, and then you're going to cross multiply. So this will multiply with the 1, and the 0.19 will multiply with the COBr2. So 1 multiplied by 4 times 10 to the negative 4 remains 4 times 10 to the negative 4 equals. This side I'm going to have 0.19 because you can't multiply numbers and alphabets, COBr2. Now, I want my BR2 to be all by itself. How do I do that? You divide both sides with the number that is irritating what you're looking for. In this case, this is what I'm looking for. What is irritating it is this number. I'm going to divide both sides by 0.19, 0.19. So this and this will cancel. Therefore, my value for CO BR2, let's calculate that. I'm going to have, oh, I lost my calculator. Okay, let me just use the one here on the side with me. I get 2.11 times 10 to the negative 3 moles. Now remember, they were looking for, this is actually another tricky part in questions because I know most of the time it's English. They say the equilibrium concentration. Equilibrium means what we find at the end. Concentration means you have to use the correct SI unit. So in this case, we're going to have mole per cubic decimeter. So which means that at equilibrium, the value that we have for the CO BR2 is 2.11 times 10 to the negative 3. And that's mole per cubic decimeter. So that is the first part of Rory Sang's question where we had to calculate the equilibrium concentration for CO BR2. But then this question has another spice onto it where it says, the second question of the question tells us that we need to calculate, let's use blue, we must calculate the percentage. We must calculate the percentage of the CO BR2 gas. They've given us a temperature that decomposed at the temperature of 73 degrees Celsius. Now, this is just a continuation from that other one, but remember now, just moving back to our previous slide, in this slide, we had gotten the equilibrium concentration. Which was this number. Now remember, when we calculate equilibrium or concentration, we use the formula C is equal to N over V. We have the concentration at equilibrium, we do not have the moles, and we do have the volume. Our volume was given to us at 2 cubic decimeters. So now we need to find our moles first, because if we can find how many moles were actually put into this container, we can then find the percentage that was actually decomposed, and that's what the question is asking us. So here we need to find what was decomposed. So the easiest way to do it, or I'm going to do it, so you can say C is equal to N over V. That's where the formula is derived. I'm going to make N the subject of the formula by multiplying it on both sides. I'm going to end up with the moles, and I'm just going to write this so that you know which moles I'm talking about of Br2. And that's going to be multiplied by my concentration and my volume. Just another thing to stress on you guys, when you are using this type of formula, you do get a mark for the formula. However, we cannot make sloppy mistakes. For an example, sometimes you guys use a capital N instead of a small n. Remember, a capital N is newtons. We're talking about Newton's laws. That's forces. A small n and a big N is two completely different things. When we use a small c, that can mean concentration. A big C means coulomb, which is in electricity. A small v can mean volume. A big V means voltage, which is again in electricity. So make sure when you do, or when you are using these equations, you use the correct symbols. I see most of my kids also do that where they think, oh, ma'am, it's just an alphabet. No, it's not just an alphabet. In physical sciences, it actually tells a story. If somebody's just looking at this, they can already maneuver and see what you're calculating. And by just mere looking at the equation, we can tell whether we're working with paper 1 or paper 2 and so forth. So let's continue. So now these are the moles that I will be looking for. I know that the concentration on the other side was 2.11 times 10 to the negative 3. The question told us that it was in a container which is 2 cubic decimeters. So let's put that in a calculator. Oh, I've lost my calculator again. Let me just use mine here. So I've got 2.11 times 10 to the negative 3, and I'm multiplying that by 2. So, and then I get, remember to say SD, I get 4.22 times 10 to the negative 3. And what am I looking for? Moles. Remember, you have to always add your moles because honestly, as an educator, if you're marking somebody's paper and they didn't write moles, you hear that cricket going crick, 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 like what were you calculating type of thing. So always make sure you have your SI unit because you do get marks for using the correct SI unit. Guys, I cannot stress this enough because some of you guys know the mathematics, you get the formula wrong, you substitute incorrectly, and you don't have an SI unit. Finding out that out of 7, even though your answer is correct, you can only score 2 marks. So always make sure you have this information. So now that I found the moles of this, I'm going to say, I'm just going to work here. I'm going to say initially, what did I have? What did I have initially? Plus, I'm also going to add what I just worked out now because now these are my moles at equilibrium, which is 4.22 times 10 to the negative 3. Initially, if we go back to our question, remember we spoke about mole ratios, that if everything is in a ratio of 1:1, so we're going to use this mole ratio because it's a mole ratio of 1:1:1. So that's where I'm getting this answer from. So initially, we have the 0.04 moles. Now at equilibrium, we have the 4.22 times 10 to the negative 3 moles. Let's see, what do I get when I calculate these two? So I'm going to have 0.04 plus 4.22 times 10 to the negative 3. And then I get a very large number. So I get 0.044. And that is the amount of moles that was now used in the system. Another thing I want to stress for you guys. Guys, if you are deciding that for every answer you're going to round off to 2 decimal places, make sure you do that for each and every one of them. If you are deciding you're going to do it for 3 decimal places only by your final answer, you're going to leave it to 2 decimal places or to a whole number, do that at the end. But don't be hunky-dory about it, where this one is a whole number, this one is 1 decimal place, 2 decimal place. Well, it's not incorrect, but we want to get to the most correct number at the end of our, once we're done working everything out. So continuing, now I've got these moles, but now going back to grade 11, we learned about percentage yield, and so forth. So percentage decomposition, required us to find what we used initially and what we had at the end. We added those two to see from this final answer how much actually decomposed. So then I'm going to say, what did I have before, which is my 0.04, 0.04, and what did I have at the end, which was this one. Remember, that's now in my moles, which will be 0.044. And you must multiply that by 100% because we are looking for percentage. If I put this in my calculator, let me do this one. So I would definitely put my whole bracket, everything in a bracket so that it doesn't get ruined off. 0.04 or over 0.044. I'm going to multiply that by 100. I get a percentage of 0.46%. So that is how much is going to decompose in this whole reaction. And this was a question by Rorisang. This was actually a very nice question. But what I'm picking up from this question, you need to go look through your grade 11, your percentage yield, decomposition, and all that stuff, your limiting and access reactants, because this is where we get that formula. So if your background or your foundation from grade 11 is a bit shaky, then this was not going to be very easy. But otherwise, you had to look at what you had started with, where you are working towards, and then kind of find what you're actually looking for.